Okay, so what we're going to be discussing today is a tree problem, and we're going to be talking about how to find the lowest common ancestor of two nodes in a binary tree. So there's a lot of flavors to this problem. There's flavors with pointers, with different things that help you do this problem different ways. So today, we're just going to look at if I get a tree and I get two nodes, how do I find their common ancestor that's the lowest? So first off, before I get into this, if you haven't subscribed to the channel, subscribe to the channel, like this video. My goal is to make this one of the world's largest resources for software engineering interviews. It might not become the largest, but we can settle for large. I think that's okay. One question that I get a lot is, how do you do tree problems? How do you get good at them? And I think I am able to comment on this because I was very, very bad. My biggest weaknesses were dynamic programming, which is something is very hard to get really good at because it's hard to see common patterns between problems because it's really hard. Tree problems, I was very bad at recursion, very, very bad. I absolutely would never solve recursive problems. And as you can see from my 3 keys to backtracking video and all this backtracking stuff I've done, I've come to a point where I understand how most of these problems work, and I'm able to solve some of these. I mean, I still get stuck, right? But I'm able to solve a lot more now. And also linked lists, which is another thing where what I'm about to say applies. So the best way to get good at those two right there is to do a lot of problems. And this kind of sucks because getting good at recursive algorithms or recursion in general is kind of useless for life at all. And you're going to probably have to sink many hours into getting good at this. But I mean, that's fine because this is for like interviewing for a job that, fruitful, it'll have a return on your investment if it's a high paying job. But yeah, that's basically the key. Do a lot of these problems. I've done every medium LeetCode problem on trees. I've probably done hundreds of recursive problems, hundreds of tree problems. Well, not hundreds, maybe 100 plus. But anyway, that's a common thing I get asked. How do you get good at recursion? How do you get good at recursive thinking? And the key is do a lot of these and you'll see problems. And again, my 3 keys to backtracking video, it didn't come from reading anything. I mean, obviously I was influenced by many resources subliminally, like underneath. But the thing is, it's just you notice patterns and you internalize deeply how a recursive function will be crafted. But all of this is besides the fact. I just wanted to make that point. We're going to be talking about the lowest common ancestor in a binary tree. And what we're going to do is we're going to look deeply at what it means to define a recursive policy for each node and how we can solve this problem if we've never seen it before. And the thing is, I definitely could not have solved this when I first saw it. And if I had first seen it now with the same abilities to do recursive problems, I still might have trouble with it. So none of this stuff is easy, but I hope this video gives you a little better understanding. So what we need to do is we need to look at some examples and see what does it mean to have a lowest common ancestor? What does it mean to find that? So let's look at some examples right now. So example number 1, this is the most common example. We have 2 nodes and find the lowest common ancestor. So this node is the lowest ancestor that is common to them, right? So this node right here, the one I'm pointing to right there, that's an ancestor of Y. Is it a common ancestor? It's not a common ancestor because it's not shared. We can't find X in a subtree below that node right there. So what is the common ancestor? That guy's a common ancestor. But is it the lowest common ancestor? Well, it is the lowest. We see that it's as low as possible. And we can find X and Y. Notice I just said find. That's a key word. We'll use that word later. Find. We can find X and Y below this node. So also, this is an ancestor of X and Y. And that node is an ancestor of X and Y. But it's not the lowest ancestor that's in common, right? They're common ancestors, but they're not the lowest. So we need to consider how recursion operates and how we can use recursion on a binary structure, a tree structure. Notice that we can use recursion run it downwards, and once we bottom out to base cases, we drill our way back upwards. And when we go upwards, we can do evaluations and do some magic, but we're gonna be able to, if we satisfy a certain property, know if I find a common ancestor and I'm going from bottom to up, the first one that I see is going to be the lowest common ancestor because of the nature of how I am conducting my recursion, right? So don't worry about this. I'm just throwing this out there because this will help us understand later. But here's example 1. Let's look at another example. Okay, so here's our next example. We have another tree, and we have x and y. But notice how the LCA lands right on x. And what we need to notice here is this is actually what it should be, right? The lowest common ancestor of x and y is a node touching x, which is x, and then the y right there. So this node right here is an ancestor of y. And the node is also an ancestor of x because the ancestor can also be the node itself. And what we see is that this guy is a common ancestor, but is it the lowest common ancestor? And in this case, it's not, because this node is above this node. We can reach x from this node, we can reach y from that node in shorter time, or I mean, that's not really the most formal way to put it, but yeah. So we saw the normal case and we saw the overlapping case. These are the cases that should come to mind kind of off the top of your head. So how do we solve this? How do we make a function to do this? And what we need to look at is something that I strongly believe will save you a lot of time when you're trying to figure out these recursive problems, trying to learn recursion in general. This is a key. Whenever I'm trying to solve a tree problem, I have a tree. What is my focus of the tree? And let me show you what you should focus on. A single node. Whenever you're doing a recursive problem, forget about what needs to happen to the whole tree. Forget about what needs to happen at the leaves, what needs to happen in the recursive case, the base case. Don't worry about any of that. This will save you so much time because this has confused me a lot of times when I tried to learn in the beginning and try to figure out how these things worked. Only focus on a single node. What needs to happen at this node for me to solve the problem? This node represents a function call. And what we're going to see is this node is the key to getting us to an answer. And what we need to do is define what I always say and call a policy, which is basically our code in the recursive function to handle just him. Given a certain state, what needs to happen at one node? That's all I care about, and we're going to investigate that right now. Okay, so let's look at a single node, and let's look at a left subtree and a right subtree. This is an overarching framework for seeing any tree problem. We'll always have a node, which we call root or we call node. We could call it anything. And then we'll have a left subtree and a right subtree. We can do anything with those subtrees. Remember, we're going from the bottom to the top. And if I hold a node and I know that I've found one of the items to my right, one of the items to my left, and they're going to be unique instances, so there's no duplicates here. What I'm going to know is what I am holding is a common ancestor. Is it the lowest common ancestor though? It has to be. Our recursion is going from the bottom upward. So what we know at that point is, if I search my left, I search my right, and I find a node here, I find a node here, either the x could be here, y could be here. Y could be here, x could be here. They're going to be unique, so we won't have an x and x. What will happen is this root must be the lowest common ancestor, right? So this is what I'm saying. If I search the left and I find x, if I search the right and I find y, this is the lowest common ancestor. I mean, it has to be. Based on our logic, based on the way we're doing this, it has to be the lowest common ancestor. And what we need to see is the other case that I just said. If we find y, and then we find x on the left, now this is kind of a key to this is a key moment that we're realizing is, again, we broke this down. We said, forget about the tree. What needs to happen at this node? What needs to happen at this node is I need to search to my left, well, this is my left, your right. What needs to happen is I need to search the left subtree and the right subtree. And what happens is if I find both, then that means this is the lowest common ancestor. That is the key case where we found our item. And what do we return? We return this node, the answer to our question. The answer to our question when we make a function call is going to be, what is the lowest common ancestor given a root of a tree and 2 nodes to find? This node is the answer. This node is the answer to that question. And we return it upwards. And again, the code is in the description. Go between this and the code to further understand this deeply. And again, you don't need to understand all of this at once. It'll internalize over time, and that's fine. So what we see is this is the critical case where we found our item. Okay, so we saw the full case. The case where I find x and then y, or y and then x, then the node is the lowest common ancestor because of the nature of recursion and the laws we defined, right? So what if we find 1 on the left and then nothing on the right? So can this node be the lowest common ancestor? It can't be the lowest common ancestor. I would have to have found the y here in this case. Or if this was y, I would have to have found the x here. Again, this can be x or y. It's just saying, do I have a value here? And if I have a value here, what that means is this node is an ancestor to one of the values, but it's not the lowest common ancestor. What we see here is that we couldn't find anything on the right. So what we do here at this node, we return the result from the left because this node can't be the lowest common ancestor. We wouldn't want to return the node we're holding. We would want to return the node to the left. So what that represents is we're saying this is the node y. From this call, I want to return that because I'm going to say from root, I can reach y, right? From root, I can reach y. So let's see the other case, and I'm going to slowly build this up to a final point I'm going to make. So we see here, found nothing on the left. If I found something on the right, that means I either can reach x or y from this node. So I don't return myself, but I return the x or the y, whatever I found, back upwards saying I can reach this value from this node. So each call, remember, represents asking what is the lowest common ancestor from this node. So what we need to string this all together because it's confusing when you see these cases individually. Let's put it all together into a little code run through so that you can see this kind of happening live, right? Okay, so what happens is we need to find the lowest common ancestor for 2 nodes and we're given a root. So there's our function right there. So what we first need to do is define base cases. When do we have an answer to a search call? We know the answer to a search call when we have null as the root. That means we can't find a lowest common ancestor. We just return null, put that right there. And we have an answer when the node I'm grabbing, we're grabbing a node with each call. Each call has a node to work with, which is root. If root is either of the values, I just return this node. I return myself because I have found what I'm searching for. I found either x or y. So let's put that right there. And what we need to do is, if neither of these are satisfied, then we need to perform a search from this node. We need to find either x or y on the left or right. So we put a search right there. And okay, what's going to happen is drill downwards, 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 recursion, recursion, recursion. It's going to keep going downwards. As long as our base cases are not hit, our recursion keeps going down, right? And what happens is we need to analyze our answer when the recursion comes back up because our base cases will get hit. And our base cases will return back up to us, and then we will have to analyze our results. Our results will come back to us because we just drilled downwards, base cases pushed back upwards. So what we need to do is look back to what we were just talking about, our cases. If I get nothing on the left, I just return what I got on the right. If I get nothing on the right, I just return what I got on the left. And I just put those there. And imagine if both come back. If both come back, then that means that the node I'm holding, we search to the right, I found something. We search to the left, I found something. That means the node I am holding is the lowest common ancestor. Remember, recursion is going bottom to top. So we just return ourselves in that case. So the whole point of this is we search, and we drill down and then come back up because of base cases, and we're going to analyze our left and right. We analyze our left and right based on the cases we define. We know what our node is. And so imagine I find both, and I'm the lowest common ancestor. I return myself to my parent, who then says, okay, I had my left and right search. I have, let's say it was on our right. I have this result, and maybe nothing comes up on the left. And what happens is the node that was the lowest common ancestor keeps getting passed upwards, and then eventually it's returned as the answer. So this is basically the understanding behind the recursive algorithm to solve this lowest common ancestor problem. And we should look at the time and space complexities right now. Okay, so let's look at the time and space complexity of this. And I drew examples so you could see exactly what I'm saying as we're looking at this. And whenever we're bounding using big O, we want to find the worst because we're trying to bound on top. We're trying to upper bound this, right? So n is the amount of nodes in the tree. And let's imagine we have a tree like this, that tree right there. We're going to bound to the amount of nodes, O of n, because we have the potential to make a call at every node. And there's n nodes, and we're going to be doing a constant amount of work at each node. We're not going to be doing anything beyond just making more calls and going downwards or upwards, if this is a base case and we just return. So the reason it's O of n is because this is a concrete example. We would drive our recursion to the left, we return back, and then we found the A, we go back up. We drive our recursion to the right, we find the B, and then we just come back upwards. And actually, those bottom calls wouldn't happen. Okay, so for the space, we have O of h for the space complexity. And before you get worried and say, oh, it should be O of n, yes, this is a case where the tree is skewed. And again, a lot of the times, we can have a worst case of a skewed tree when we're doing these tree problems. And what happens here is we have 4 nodes, and we're looking for the lowest common ancestor. And it turns out it's right there. But what we would have to do is we'd have to go all the way down, touch all of these guys, and each of these is another call on the call stack. The call stack is going either upwards or downwards, depending how the system implements it underneath. But what happens here is n is 4. What is the height of the tree? It's 4. N equals h. So it's not, I don't want to say safer because you want to know exactly what you're talking about and saying, to say O of h because, yeah, n can be h, or h can be n in the worst case. H can be n because these are the same, worst case. Or we might have a normal case where O of h is correct as well, but O of n would not be correct. So O of h is a better way of saying this because it takes into account the very normal cases and then the skewed case. But both are equivalent. Both are saying the same thing. If I said O of n, O of h here. So those are the time and space complexities for this problem, or this variant of this problem. And yeah, that's basically it. All right, that is all for this video. We discussed finding the lowest common ancestor of a binary tree. Again, there's a lot of variants to this problem with pointers and a ton of other stuff. This is just if we got a raw tree and we have to do searching for these nodes and to find their lowest common ancestor. This is one approach to this problem. You could increase the space and use a hash table and all that stuff, but we can save that for another day/lesson. So if you have not subscribed to the channel, subscribe to the channel and like this video. My goal is to make this a very large resource for software engineering interviews and to help as many people land the jobs that they like as possible. And yeah, that's kind of what this stuff's for. I don't know why I'm still doing it and like how this kind of started, but I'm just rolling with it. And oh yeah, And this room is kind of, it's not like the nice room we have with the like glassy whiteboards. This is like it's like lower quality, like it's the middle of the day, and normally I record at night in the other place. But yeah, this will suffice for today. And